Mm-hmm.
Hello everyone, I hope you're doing well. In this video, we are going to find out the commutation relations between the position operator and momentum operator. Here you can see only 3 commutators, but I'll be doing more of these. You will see at the end of the video. And this video is really important if you really want to understand the commutation relations between position and momentum operator. First of all, we'll see the commutation relation between the x position and x component of momentum operator. Here y component of position and y component of momentum operator, and similarly like that. And I'll be doing one more case in which we'll see that what does this commutation relation equals to for a case when we have, let's say, y position operator and some different momentum operator, let's say x momentum operator. So out of curiosity, we'll see what does this equals to. And let me tell you that commutation relations are really important in uncertainty principle and also in general context in quantum mechanics. They tell us a lot about the relationship between two different operators and observables. So momentum and position operators are always on the highlight, we know, in quantum mechanics. So well, let's quickly get started with this commutation relation and calculate what does that commutator equals to. And first of all, I write down the general formula. We know that the commutator of two operators is given by, let's say the two operators are a and b. Okay, so commutator of a and b, that is equals to a b minus b a. Okay, it's the product of first operator with second operator minus the product of second operator times the first operator. Okay, so that is what the commutator is equals to. And we can see the representation, there are the square brackets in there, and if these brackets are used in question, then it means that it's anti-commutator, it's not commutator. In commutator we have these square brackets. This representation is for anti-commutator, and anti-commutator actually equals to a operator times b operator plus b operator times a operator. Okay, so keep that in mind, keep that differentiation in mind, that representation changes, hence the formula changes. And you must be aware of these two different kinds of commutators, like one is commutator and the other is anti-commutator, and this is anti-commutator representation, and that is the formula for it. And we are calculating the commutator since we are using the square brackets, and hence it's clear to us. And let's quickly get started with this. We have x operator first and then position, oh sorry, momentum operator, and we will write it to be equals to first operator, which is x, second operator, which is px, minus second operator, which is px, times the first operator, which is x. Now you are supposed to apply psi function on both sides. Okay, this is psi wave function that we need to apply on both sides, because otherwise you can't simplify operators without applying them on any wave function. You can only observe the effect of operators when you apply them on some wave function. You can't observe them or test them, you can't test their simultaneity all alone. You have to apply on some state function. So let's say psi is some state function. We have, let psi is the eigenfunction of the commutator. All right, that is the critical step. Keep that in mind. We'll be applying psi whenever we are supposed to calculate the commutation relations or commutators. So let's simplify it. We have x operator px hat multiply psi with it, so psi will appear on the right hand side. Px x hat applied on psi. Now what is x operator and what is px operator? X operator is simply the x operator, but px operator is actually equals to minus iota h cut partial by partial x. So let's put this value into this expression. X operator, px operator, psi, that is equals to x operator. Okay, in place of px operator we'll be writing minus iota h cut partial by partial x times psi. In place of px, I'm again writing minus iota h cut partial by partial x, then x operator applied on psi the same way. And here minus iota h cut is, it's a constant, so we can take it outside, and we have x operator applied on partial by partial x psi. So it's partial psi by partial x. As a result, minus minus plus, this is iota h cut. Then we have partial by partial x and x operator applied on psi. Now let's simplify these operators. Keep that in mind, since when position operator applies on psi, it comes to be x times psi, simple x times psi, nothing changes. So we'll write x psi in place of x hat psi here, and partial psi by partial x remains the same because we doesn't have any psi specifically, so it will remain the same way. And also when x operator now is applying on partial psi by partial x, so the similar thing will happen, that it would be equals to x times partial psi by partial x. Simply nothing will change, we just change x operator into x. Minus iota h cut, it's x partial psi by partial x. You don't need to simplify it any further. And iota h cut partial by partial x into x psi. Now we can see here that we have two functions now, one is x and the other is psi. Partial by partial x is applied on these two functions, so we'll be using the product rule of differentiation. To simplify it, iota h cut remains the same. So let's say this is the first term and this is the second term. First term as it is, derivative of second term, plus second term as it is, dot derivative of first term, partial by partial x of x. Partial x by partial x is 1, so it goes to 1. And yes, now it's minus iota h cut x partial psi by partial x plus iota h cut x partial psi by partial x plus psi, simply. Now what we can do here is to multiply iota h cut inside, so it's with this quantity and with this quantity as well. Let's do that. Plus iota h cut, when it's multiplied with the quantities inside, it's partial psi by partial x, it's partial, plus iota h cut psi. And here we can see that it's negative iota h cut x partial psi by partial x, and it's positive iota h cut x partial psi by partial x, so they cancels out and we are left with iota h cut psi. And we had x hat px hat psi, that is equals to iota h cut times psi. As you can see here that it completes the eigenvalue equation, in which when operator, which is actually the commutator, applies on psi wave function, a constant terms times psi wave function comes back. It means that this commutator is actually equals to iota h cut. Alright, so that is what we needed to calculate. This sin psi neutralizes and we have this thing at the end. Alright, and what happens if you replace px, like if we have px first and x second, then what happens is that only the sign changes, like we will have minus iota h cut. Okay, so nothing else changes. Let's calculate this commutation relation now, and the process is really easy. We know that this commutation is actually first operator times second operator minus second operator times the first operator. Alright, this y is in subscript of momentum. Applying the commutator, this commutator actually, on psi wave function. Alright, so let's apply this commutator on psi wave function to see what does that commutator actually equals to. And we have py operator to be equals to minus iota h cut partial by partial y this time. If it's y, there will be y here. If it's x, it will be x here, and so on. Let's do that. Y operator, py operator, let's multiply psi first inside, so it's psi with this quantity and psi with this quantity as well. Y operator, instead of py operator, we'll be writing minus iota h cut partial by partial y, and it is applying on psi minus iota h gut partial by partial y instead of py, then y operator applied on psi. We can simplify, it's minus iota h gut, we can take it out, and it's minus iota iota h gut, then operator partial by partial y applied on psi minus minus plus, so we have iota h gut partial by partial y applied on this thing. Here partial psi by partial y cannot be solved any further because psi is not a particular, particularly defined wave function, it's in general. So partial psi by partial y remains the same, it's a quantity now. And here what we have is that y operator applies on psi. So what does that equals to? It simply equals to y times psi, simple y times psi. We can replace y operator times psi with this quantity. And also here, when y operator is applied on partial psi by partial y, it is equals to y times partial psi by partial y simply. So let's put this value right into this expression, and we get minus iota h gut y partial psi by partial y plus iota h gut partial by partial y applied on y times psi. Okay, now we can see that we have two quantities, y and psi. Partial by partial y is applied on these two quantities, so we'll use the product rule again to calculate it. Let this be the first quantity and let this be the second. Using the product rule of differentiation, we will get derivative first term as it is, derivative of second term plus second term as it is, derivative of first term. Okay, that is the product rule of differentiation. And minus iota h gut partial y by partial psi by partial y plus iota h gut, and we can multiply iota h gut with these two quantities inside, and we have iota h gut y partial psi by partial y plus iota h gut psi, and partial y by partial y is 1, so we are left with this quantity. Now we can see here that it's minus iota h gut y partial psi by partial y, and it's plus iota h gut y partial psi by partial y. They cancel out to be 0, and we are left with iota h gut psi, and we had y operator, py operator applied on psi, that is equals to iota h gut times psi. We can see when the commutator is applied on some psi wave function, some constant quantity times psi wave function comes back. It's the eigenvalue equation, and psi just neutralizes, and hence we can write the commutator is equals to iota h gut. As we can see that this is also equals to the commutator of x and px operator. All right, this was also equals to iota h gut, and you can confirm that y operator, py operator, commutator of position operator and momentum operator, and also for z case, they are all equals to iota h gut. Okay, they're all equals to iota h gut, and it happens, it's positive iota h gut when you have position operator first and momentum operator second. It will be equals to negative iota h gut when you write the momentum operator first and position operator second, like that. We'll test it right away. Okay, I'll test it for this third one. It will be equals to negative iota h gut. It just changes the polarity sign when you shift the operators. So that is it. Now let's do it for this one case, so that you may confirm that how does this happens. So pz operator and z operator, let's find out this commutation relation applied on psi, that is equals to pz operator z operator psi minus z operator pz operator psi. We know that pz operator is minus iota h gut partial by partial z operator applied on psi minus z operator as it is minus iota h gut partial by partial z into psi. Okay, now minus iota h gut can be written like that, partial by partial z. We know that z operator applied on psi is actually equals to z times psi. Simply this minus and minus becomes plus. Iota h cut could be written outside since it's a constant. Then z operator partial psi by partial z. Now z operator applied on partial psi by partial z is simply, you know. Okay. First, let's apply the product rule on these two quantities first, and this is the second quantity. So first term as it is derivative of second term plus second term as it is derivative of first term plus iota h cut. We can write z partial psi by partial z because position operator just applies and comes back as nothing happened. So that is what we have. Now let's multiply minus iota h cut inside, and we can see this is partial z by partial z, that is equals to 1. So it's 1 in here, multiplied by psi, so it's psi simply. So let's multiply minus iota h cut inside and see what happens. It's minus iota h cut z partial psi by partial z minus iota h cut psi into 1 plus iota h cut z partial psi by partial z. We can see it's minus iota h cut z partial psi by partial z, and it's plus, so they cancel out, and we have minus iota h cut times psi, and it was p z operator times psi, that is equals to minus iota h cut psi. Hence we have p z operator z, that is equals to minus iota h cut. Alright, so this is how we can calculate the commutation relations, and let's do it for the last set that we had, and it was y operator applied on px operator. Okay, let's see out of curiosity that what does that equals to. Applied on psi, that is equals to, we have y operator first, then px operator applied on psi minus px operator times psi, y operator on psi. All right, now we have px operator to be equals to minus iota h cut partial by partial x. Keep that in mind, it's partial by partial x that matters. Okay, so we have y operator minus iota h cut partial by partial x into psi minus iota h cut partial by partial x y operator applied on psi. We have y operator applied on psi to be equals to y times psi simply, and so y operator, okay, this minus iota h could be written outside, so let's write it. Minus iota h get outside, y operator applied on partial by partial x psi, so it's partial psi by partial x simply, minus plus iota h get partial by partial x, and we can write y times psi simply here. Now keep that in mind that y is treated as constant when its partial derivative is with respect to some other variable. Okay, so y would be taken outside because y is taken as constant in partial derivatives of x and z. All right, that happens in every case. If you have partial derivative, then only the variable with respect to which you are finding out the partial derivative is taken as variable. Rest of all the quantities are treated as constants. Okay, keep that in mind, but this doesn't happen in full derivatives. In full derivatives, which are, let's say, d by dx, you treat y as variable, but not in partial derivatives. Okay, you take only that variable as constant which is for which, with respect to which you are finding out the partial derivative. So y will be taken as constant, it will come outside, so we have partial by partial x into psi, and we can see here that it's y operator applied on partial psi by partial x, which is simply equals to y times partial psi by partial x, because that is the thing with position operator, they come as it is. So you can see they are both equal and they are equals to 0. They cancel out and it's equal to 0, and we can see that this commutator is actually equals to 0 times psi. You can write times psi. Okay, so you have y operator, when it's applied on x operator of momentum, the commutation relation is 0. Let's summarize all of these commutation relations between the position operator and momentum operator and their different components. And we have seen that commutation relation between x component of position and x component of momentum, y component of position and y component of momentum, and z component of position and z component of momentum, they're all equal to each other and they are equal to iota h cut. All of them are equal to iota h cut. If you change the order, if it's first the momentum operator and second the position operator, what happens is that we have negative iota h cut. Okay, sign changes, polarity changes. Now if we have commutation relation between x component of position and y component of momentum, for example, or x component of position and z component of momentum, they will be equal to 0. Okay, if you are finding out the commutation relation between different dimensions, if it's y for momentum and x for position, x for position and z for momentum, and any mix of it, they are equals to 0. Similarly for z, or any mix of it. Okay, if you find it out for any mix of it, like even for x and y, this commutation relation will be 0. For y and z, the commutation relation will be 0, and so on. All right, so if you are finding out the commutation relation between different dimensions, they will all be 0. It is because the perpendicular dimensions, the independent dimension doesn't interfere with each other, so they doesn't make any difference. If you're finding out the x component of position first and z component of momentum, they will not interfere, and that the order doesn't matter. So you can see here all of these commutation relations are 0, and only those commutation relations are non-zero which are happening in the similar dimension. That is it for this video. We'll be finding out more of these commutation relations in next videos, so stay tuned, keep watching, and take care. Goodbye.